is a school of maths and physical sciences, and there are physicists in the room. So Peter is a physicist, a theoretical physicist by training, and I'm a pure mathematician by training, but this talk is about biology. So I think, like, if there's, and the level I'm going to talk at, I'm hoping that I'm going to make this accessible. So the mathematics, I do have a couple of proofs, but the maths is very combinatorial. I don't think you'll find it challenging. So I hope nobody's alarmed. I do mention semigroups at some point, but I wave past them in a touristy kind of way. So now, why would that not work? This is one of those things that was working perfectly before.
Maybe I'll just switch a slide. Oh, yeah.
Oh, maybe it was just the focus was, yeah, here we are. Okay, excellent, thanks. So this is the map of the talk. I'm going to talk about binary trees and matching, so binary phylogenetic trees and matchings, matchings being matchings on a finite set. And then I'll talk about some extensions to that we've worked on and some algebraic opportunities. But first, I'm going to start with an introduction so you all know what we're talking about. I think the thing is that I would like to sort of communicate is that there are lots of interesting questions in evolutionary biology that are not immediately obviously accessible to people with different toolkits, but if you spend some time, you can find some fun problems. So I'll start with an introduction. So phylogenetics is simply about trying to explain the relationships between species. And I guess that's crude because sometimes you're talking about viruses or bacteria, which species are not very well defined. But certainly originally back in Darwin's day, it was about species. And so this picture is from Darwin's notebooks and is perhaps one of the most common tattoos you find at phylogenetics meetings. People literally, I've seen several people with, I think, tattooed on them from this, which is lovely, I think. So he was thinking about physical observations. So how wrinkly pea pods are, the shape of a bird's beak, to try to draw connections between species and think back to common ancestors. So if you collect a set of species like this, then he's hypothesizing that there's some common ancestor, and the distance in time from these species to other species is less, so they're more closely related. And he can't tell here where the order of speciation might have happened. He just can see that they're sort of clumped together as a set of species. And nowadays, of course, we use mostly genetic methods. So people will do a multiple sequence alignment of a whole bunch of species, and they'll have some evolutionary model which says how the DNA changes. And there are lots of different ways you could do that. And so there's lots of work there for people who like thinking about processes and statistics, of course, as a whole, because the data are huge. So there are lots of different ways of taking something like a multiple sequence alignment and producing a tree. One way is to, a very simple way, is to have a distance function on the set of species. So you take some information about the DNA. It might be the arrangement of the genes, for instance. If you're, say, with in bacteria, this is a common thing to do because the genes get shuffled quite a lot. So you might have a distance method that tells you how far apart the species are, and then you create a distance matrix, and from there you can construct a tree. And that's actually how I got first interested in phylogenetics, because I was working on genome organization in bacteria with a collaborator at UNSW. And I heard a talk by a guy from UTS called Aaron Darling, and he said something like, we looked at the rearrangement process of genes on bacterial genomes using signed permutation matrices. And what he was looking at was DNA has an orientation. So when you flip two, you've got a reversal, a swap of two things, but you also have an orientation reversal. And I grew up with permutation groups, with reflection groups. And so signed permutation matrices, I thought that's a type B Coxeter group. That's a hyperoctahedral group, and that's my thing, so I started working on that and looking at that. So from a group theoretic point of view, I'm not going to talk about that today, but that sort of approach is a common approach. The second one is to do something more statistical and have run some process, evolutionary process, which involves mutation and speciation. And then you sample from tree space to try to measure the best tree that fits your data. So there's a need sometimes to be able to search over tree space. So again, that's you probably get an MLE for the best tree that fits the data. So what are we talking about? I'm going to talk about rooted trees. So not Darwin's picture was an unrooted tree. So this is a tree with a root. It's got every vertex has in degree 1 except the root, which is the one at the top. And everything has out degree 2 except the leaves, which are the ones down the bottom. So the leaves are the species, and I'm going to just label them 1 up to n. And if you've got out degree 2 for everything except the leaves, it's called a binary tree. And if you allow more flexibility, so you can have a higher degree, it's often called non-binary, which is an unfortunate terminology, not because this means something different mostly now, but because it includes binary trees. So the class of non-binary trees includes the binary ones. So I'll try not to use this, I'll try to say all trees. But one thing to note is that we don't allow vertices of degree 2 inside the tree. So you won't have like vertices on a branch like that. And one reason for that, biologically or inferentially, is that if you think about inferring things from data, when you're trying to infer a tree, you have information about the present. You have information about the species down here. You don't have any information about the past. That's all what you're trying to infer. So what sort of information would you need to try to infer a node that's stuck there in the middle of a branch? And basically, there's nothing I think that you could have that would tell you about that, except perhaps a fossil record. Maybe if you had a fossil record of something, so you had data that was back in the past. But anyway, for our purposes, we're not going to allow those. So I said this is going to be a combinatorial talk. So this is really just a very old result about counting the number of such trees. There are 2n-3 double factorial of them when n is the number of leaves. So the double factorial just means it's the product of all the odd numbers up to 2n-3. So the proof actually looks at the unrooted trees. So if you start, I think you need to start with n equals 3 for this to make sense. And so you can count the unrooted trees as 2n-5 double factorial, count the number of edges as 2n-3. So that's going to be left as an exercise. But then an inductive step is kind of simple. You take an unrooted tree on n leaves and you add another leaf by adjoining it to one edge to create a tree on n+1 leaves, and you've got 2n-3 edges to choose from. So you've got 2n-3 extra options for each one of the original trees. I guess there's a little bit of work there to convince yourself that you're getting new trees every time, and that really gets you all the trees. But it's not a very complicated argument. And then you can go to the rooted case from an unrooted case by choosing an edge to put the root on. So if you know how many edges there are on that unrooted tree, then that's how many choices you have for a root. So you can get the number of rooted trees. So I know I've rushed over that, and you're probably thinking he's missed a few details, but that gives you a flavor of what sort of proofs are there. So I think you could set this in an undergraduate combinatorics course if you wanted to, which isn't to say it's easy, because combinatorics is harder than it usually looks. So the paper that got us, Peter and I, thinking about these problems that I'm telling you about today is a paper by Percy Diaconis and Susan Holmes in PNAS, Proceedings of the National Academy of Sciences, in 1998. So their paper was called something like Phylogenetics and Perfect Matchings. I may have that wrong, but it's something like that. So they just pointed out that there's a one-to-one correspondence between those binary phylogenetic trees that I described and perfect matchings on 2n-2 elements. So n-leaf trees, matchings on a larger set, 2n-2 elements. A matching is simply a partition of the set into pairs. So you take the set and you break it up into pairs. And if you've covered the whole set, then that's a perfect matching. If you've got a subset, it's just a matching. So there's phylogenetic trees, binary phylogenetic trees are perfect matchings on a larger set. And this talk is going to go in two directions from this, the extensions and the algebraic thing. We actually started with the algebraic direction, but I'm going to tell you about that later. So let me tell you about how this matching goes. You first number all the internal vertices. So the key is that there are 2n-2 internal vertices in total, excluding the root. There's 2n-1 altogether, but we're not going to worry about the root. So there's an algorithm for labeling the internal vertices, which I'll tell you about in a moment. And then you can think about vertices that are siblings. So sibling vertices are those that have the same parent. So if I just flick back, it's too far. These two are siblings, that's their parent. These two here are siblings, that's their parent. So that gives you a matching. Yeah.
Can I just ask a question? So why is the answer not the Catalan numbers? Is it because the trees are not ordered?
The Catalan numbers are for, I think that works for trees where you have all of the vertices labeled. Not just the leaves. Yeah.
So the trees are not ordered.
The trees are not ordered.
It's not fine. They're not. You can move them around.
Yeah. You can. Yeah. So this is Peter Erdos, not Paul, and Laszlo Shekeli provided this algorithm for labeling the vertices, and it goes like this. So you look at the vertices whose children are all labeled. So here you've got 2 and 3 and 5 and 6, and you choose the one with the lowest label among the children to put a new number on. And then you've got now 1 and 7 and 5 and 6. So this one is the winner, gets the label. And now we only have one pair to choose from, and so on. So, and then we've got a matching. So the matching is the pairs of siblings that have a parent, share a parent, 4 and 9, so on. Okay. So the reverse direction also works. I won't do it here, but what you need to be able to do is go from perfect matching to first to find n, but you know that this is of 2n-2, so it's easy to find n, and then you can reconstruct it. So I guess the non-trivial part of going backwards is knowing that you will always have a pair that that you can join together to add a parent of. So that's binary trees and matchings. Let me tell you about extensions. So the extensions go from binary trees to non-binary trees and also forests. So forests are just collections of trees. So you can still do the labeling of internal vertices. That algorithm works exactly the same, except you no longer have pairs, you might have larger sets. And there's, of course, no longer n-2 internal vertices. There can be any number. So the corresponding result is that all rooted phylogenetic trees, binary and non-binary, is in bijection with the set of partitions of finite sets into components of size 2 or more. okay, because you don't have vertices that are on their own with parents. So every vertex, internal vertex, has a sibling. So you've got components of size greater than or equal to 2. And this one is very general. All rooted phylogenetic forests is in bijection with a set of partitions of finite sets. So I got very excited about this. I mean, you can imagine the proof is not very difficult, and there's some technicalities in there. It's all about, like I said, knowing that if you give me a partition of a finite set, that I can reconstruct the tree, that I can get backwards. It's easy to go from a forest to a partition of a finite set, but knowing that you can always go backwards, well, I guess it's not terribly hard. It's more like a lot of careful applications of the pigeonhole principle. But so it's not like, I didn't use perverse sheaves or anything. It was elementary in some sense. Yeah, so let me show you how this works. So here's a forest, and you'll note it's not binary. It's got a couple of triplets here and one, and those two, there's I guess out degree 3 vertices in a couple of places. So the numbering algorithm goes the same. You look for sets, not pairs anymore, but sets of siblings that are all labeled. So I've got 2, 3, 5, 6, 7, and 4, 9. I pick the one with the lowest label, and then I continue. And I think 4 and 9 should be next. Now I've got, you have to be a little bit careful, 8 and 11, but it's not difficult. Again, it's something you could get a computer to do for you. 5, 6, 7, and now I think I've got 1, 10, and 12. So here I'm going to label all the roots except 1. So one vertex will remain unlabeled. And there I get a partition of the set 1 up to 13. Okay, and now I'm allowed to have sets of larger than 2 elements and singletons. And the singletons are now labels of root vertices of some of the trees. Okay, so to go backwards, it's slightly more complicated because if you give me a partition like this, I need to know what n is. And before I knew that if I had a perfect matching, that there were 2n minus, and it was a binary tree, then 2n minus 2 was the number, so I could easily work out what n was. And now I don't know, but there's this. I'll prove this on the next slide. It's not very difficult, as you'll see, but this is the size of the partition. So this is the number of distinct elements. This is the number of sets that have 2 or more elements in the partition. And that's the number 1. So quick proof of this. You simply count vertices in 2 different ways. So again, a classical combinatorial technique. So every vertex is labeled except one of the roots. So the size of pi is the number of labels. So the number of vertices in total is the size of pi plus 1. That's counting it one way. And then the other way is to split it into leaves and non-leaves. So there are n leaves. And this counts the number of non-leaves. So every non-leaf corresponds to its set of children. And that's a set of size greater than or equal to 2. So that's the non-leaves. And so you have the size of pi plus 1 is n plus the number of components of size greater than 2, greater than or equal to 2. And that's rearranged into that. So if you have a partition of a finite set like this, you can compute these numbers and figure out what n is, and then reconstruct the forest in the same sort of way. So if you're thinking about trees or forests, you're thinking usually about the number of leaves, the species. If you're thinking about partitions of a finite set, you're usually thinking about the size of the finite set. So if you've let the binariness fall away, you no longer have you no longer know what n is. So if you have a finite set of a partition of a set of, say, size 13, like we had, you can have a wide variety of different n values. So if I were to take all the partitions of 13, then I would have trees and forests of different sizes and shapes. But in phylogenetics, you often want to think about what am I corresponding my trees or forests with n species to? So unfortunately, it gets a bit lurky. So if I just say this is, I'm going to have a size condition. It might be that the partitions have 2 elements, the sets have subsets have 2 elements exactly. It might be that they have more than or equal to 2 elements, or there might be no restriction at all. So let's let lambda k be star be the set of all partitions. And this is going to indicate the ones that correspond to trees of size n. So you can see this condition here is the one that is the condition on pi that gives me n leaves, precisely. So this is just that set of partitions that give me things with n leaves, whether they're trees or forests. So my conditions are things like this. So they're either all the subsets are size 2, or they're greater than or equal to 2, or they can be any size, and I've got binary trees, all trees or forests. So I get this nice diagram. This is really for the category theorists. So this is the rooted phylogenetic binary trees on n leaves. This is the same, but without the binary restriction. That's forests on n leaves. And this is my partitions of 2n minus 2, where star, the condition is that all sets are size 2, the perfect matchings. This is the larger set that allows the non-binary trees, and this is the one that gives you the forests. So I get a nice little landscape for phylogenetics and sets, partitions of sets. So let me tell you a little bit about the algebra. So in the 1998 paper of Diaconis and Holmes that piqued our interest, they said a different method, they're referring to finding optimal trees, maintains a set of potential trees, choosing 2 at random and creating 2 new trees through a tree reproduction scheme. It's a bit like some sort of Monte Carlo method of moving around a landscape. And so they were proposing, so let me finish maybe. Algebraists have introduced a method for making a product of 2 matchings, which is known as the Brauer algebra. This enables a simple implementation of a genetic algorithm. So what they're proposing is, if you're trying to randomly move around space, you have to think about what you mean by random movement. And so there are lots of games phylogenetics people play to move around tree space. They take branches off here and they shove them over there, and they do sort of random things. But this allows, perhaps they were positing, a different way to move around tree space. You convert the tree into a Brauer diagram, and I'll show you what that is in a moment. And then you multiply them, and then you sort of get some new tree. And maybe that's a different way to move around tree space. It's certainly a quick and easy one. So this is what a Brauer diagram looks like. It's got 2 rows of nodes that are labeled by the elements of your set, and you draw connections between the ones that are in subsets together. So 1 and 7 are connected because they're here as a subset. 2 and 3 are here as a subset. So that's a Brauer diagram. And if you've seen, there's a whole ecosystem of these sort of diagrams. So if you've seen braids, you've seen things like this with crossings allowed, like where the strings go over and under. If you've seen Temperley-Lieb algebras, there's similar things where you don't allow crossings at all. Yeah, so there's a whole world of tangles and things like that this relates to. So this would allow you, because remember, this is a tree. This is a tree that's now a partition. This is a binary tree. It's now a partition. I can draw the binary tree like this, and you give me another tree. I can multiply them together. The way to multiply them is you just concatenate them. You just put them underneath each other, and you join the lines. And if you get loops, you throw them away. If you're really a Brauer algebra person, you carry around a lambda or something to indicate the loops that you've deleted. But so I guess what Diaconis and Holmes were thinking was, you know, it's a thought bubble. It's a very nice thought bubble. But and when Peter and I saw this, we thought that's a really cool thought bubble, because he's, like I said, a theoretical physicist, and I worked in reflection groups and also braids for a while. So this is like great. Isn't it wonderful if you can find a way to use maths you know a little bit about? So we thought about using the lambdas in some way as well, because maybe there's some information there that you could carry, but we didn't figure out a way to do that yet. But the problem with this view of things really is that what is the biological meaning of that diagram? And the problem from my point of view is that these nodes have particular meanings on the tree. So 1 up to 6 are all the leaves. So 6 is somehow preferred here. It's got some special status. But in the tree, it doesn't have any special status. It's just another leaf. So this is somehow skewing things in a funny way. And so the obvious solution is to give up having the same number of nodes on the top and bottom. So these are also a studied mathematical object, unbalanced Brauer diagrams. And so now I've got all the leaves up the top and the internal vertices down the bottom. And so instead of having this tree connect to that, this tree is now this diagram. So now what can I do with that representation of this biological information as a Brauer diagram? So I have certain features that I can point out. So in phylogenetics, these things are called cherries because they look like pairs of cherries hanging down. So cherries here are the cups that are along the top. So that's, if you have to imagine everything's flipped over. The leaves are down the bottom here and up the top there. And there's a concept called the rank of a diagram, which is these transversals, these arcs that go all the way through. And you've got some simple relations. This is really just counting the vertices along the top. Everything that's along the top is either a cherry, in which case there's 2 in that cherry, or it's a transversal. So once you've got, okay, so you've transformed tree space into some unbalanced Brauer diagrams. And I am restricting my attention now to binary trees. So the other cases are, you know, future work, I guess. If you've got a set of these diagrams, your tree space is now a set of diagrams. You can move around the tree space by acting on the top or bottom by elements of these Brauer monoids. So you've got a monoid. We're not thinking about the whole Brauer algebra. We're not really considering adding these things together. Although I bet there's some way to make meaning out of that. But for the moment, we're just thinking about the monoid. So the set of these diagrams, Bn is these will be the Nn ones, and n-2 is the n-2, n-2 ones. They form a monoid because you can multiply them together. It's an associative product. There's no inverses, and there is an identity. So it's a monoid. And you've got these symmetric group elements, and you've got these cups and caps. So you can act by the symmetric group elements, you can act by the whole business, and you get nice little features like, so actions by the symmetric group preserve the rank, which means they preserve the number of cherries in a tree. So they're preserving some topological property of the tree that biologists care about. So how does this work? For instance, here's a tree, and here's a generator of the symmetric group acting on it, and I get a new tree. So all that's happened is I connect the arcs around. And so my tree, in this case, I've acted by the transposition 3, 4, and the effect on the tree is literally swapping 3 and 4. And I have to produce a better example of this because sometimes it doesn't work so nicely. You might say, oh, does acting by the symmetric group always just permute the labels on the leaves? And unfortunately, no, it doesn't, because sometimes you've got to remember these internal vertices are labeled by an algorithm. And so you can swap some of these things down the bottom, which change the labeling on the internal vertices and mess the tree up a bit more. So it is when I say mess it up, makes it more interesting. Okay, so I said the word monoid, and so that's monoid is a kind of semigroup which has an identity. So once you've got semigroups, you've got a whole lot of structure in semigroup theory. So there's a set of relations called Green's relations, which are an equivalence classes on semigroups, equivalence relations. So the first one is the L relation. There's an L, R, D, and H. Now, I'm going to flash this slide in front of you and the next one, and then we'll move on. So don't worry too much if this is not familiar to you. But they're not, the idea is that two, I'm calling them trees now, they're trees / diagrams. They're related, all related. If one can get, you can get the T prime from T by acting on the left. And they are related if you can get to T prime from T by acting on the right, by alpha. So the left related and right related things. And then in semigroup theory, this is a standard way to decompose a semigroup. But we're using restricted Green's relations. So for those of you who do know about Green's relations, I'm only going to consider actions by the symmetric group because they're nicer and things behave better. So I'm saying they're left related if there's an element of the symmetric group which takes one to the other. The D classes are the big equivalence classes that two trees are related if they're L or R related, and the H classes are the little ones, the intersections. They're H related if they're left related and right related. So the thing about this, this is a D class you're seeing, is that there's a lot of structure that has biological relevance. So the L classes are in the rows and the R classes are in the columns. So the things that are in the L class can be reached from each other by action on the left, which for us is on the top. If you take a diagram, a Brauer diagram, and you act on the top, you don't change what the bottom looks like. The caps on the bottom stay exactly where they are. The transversals stay exactly where they are. So these are the sort of bottom halves of the diagrams. They sort of represent the L classes. And the top halves of the diagrams represent the R classes, because when you act on the bottom of a diagram, you don't change the shape of what's up the top. So then you've got these H classes in the middle, which are the diagrams that if you were to cut them in the middle, across the axis in the middle, they would look the same on the top and the bottom. And all you've got is those transversals that move around. So here there are two transversals. So you've got a class the size of S2, symmetric group on two things. If you had three, you'd have 6 diagrams in here because you have 6 ways of connecting the two. So you've got these two trees that relate to that in the same little H class. So you've got a way to break up your whole tree space that is it's just different to any other ways that tree space has been broken up previously. So if you take the whole tree space or the whole of any semigroup, you can break it into the D classes and then smaller ones. This is one D class. This, if you have binary trees on 6 leaves, there are precisely 3 D classes. And if you note here, the number of transversals is 2 in all of these diagrams. So this is D4. Oh, sorry, this is D2. There are 2 transversals. This is a much smaller class with 4 transversals. You can imagine if there are 4 transversals, there's not much room for movement. The cups and caps are constrained. And this is when there are none. So everything is cups and caps, also more constrained. So that's to be like, there's a lot there to explore and we don't really know what to do with it yet. We're still at that stage. One thing that we did think about was, unbalanced diagrams don't allow you that nice multiplication that that I showed you with early on, like with when Diaconis and Holmes wrote that little remark, they were thinking about just multiplying diagrams. But so you would think that you can't multiply diagrams that are unbalanced, but you can if you define something called a sandwich semigroup, which is why there's sandwich in the title of the talk. So what you do to define a sandwich product, you've got two unbalanced diagrams. You have to multiply them relative to a third diagram. So you take some third diagram and you flip it and you put it in the middle, and suddenly you've got a product that works, that is defined. So this is a product relative to a tree T. T bar means I've flipped it over. So I've just, I multiplied T1 and T2 relative to the third tree T. So that's a semigroup that is, I don't know how well studied, but it is quite well studied. I think it's reasonably recent developments, but there is a lot of work gone into studying sandwich semigroups. So I'm hopeful. And there are a whole lot of other then semigroup questions that a semigroup theorist would ask. And so we did, of course, talk with a semigroup theorist. So one of my colleagues is a guy called James East, who is really great at semigroup theory. And so he helped us a lot to understand some of these structures. So what I like in semigroup theory, idempotents are super important. So they're the elements that multiply, that square to give themselves back. So E squared is E. So they're super important for semigroups. I'm just really curious, if you have a sandwich semigroup relative to, you give me your favorite tree, T, and I define the sandwich semigroup relative to that tree. Yeah?
Sorry,
Yeah.
define regular.
I didn't define regular. I don't want to define regular. It's something to do with, and the reason I don't want to define it is I always forget the technical definition. It's something about the product of ABA. It's sort of like AAB equals A or something like that for all AB. So there's a condition. So a lot of semigroup theory I find like this, and it confuses me, so I forget it. But there's some condition about, like, identities are defined differently in semigroups, for instance. Well, see, Ross, that's not fair. That's not a fair question. I just said I was confused about semigroup theory. So the question for those of you on Zoom was it von Neumann regular? I don't know. Sorry. Yeah. I'll have to look it up. Yeah, so the idempotents are important in a semigroup. And so I want to know what, whether there's information about the trees that are idempotents in that semigroup relative to T, because that does define some sort of neighborhood related to T, a smaller subset of tree space relative to T. But we don't know, and I think that's quite a difficult question. Okay, so I was talking about the Brauer diagrams in relation only to binary trees. So you can draw diagrams for any partitions. There's a thing called a partition category and partition monoids. And so you can draw partition diagrams for your non-binary trees and for your forests as well. So this is this forest that we saw before. So this is the partition from the forest. You work out the number of leaves and you put them along the top, and then you've got your diagram. So these edges, you know, if you were pedantic, you might say, okay, 1, 12, and 10, that's an equivalence class here. It's a subset, so they should all be connected, and yeah, they should all be connected. But you know, you tend to just draw the ones to. It's a transitive relation, so you just imagine the extra connections. And the multiplication does work if you take transitive closures of sets. And then you can act on them in the same way. We haven't studied this yet, but that's to be done. So now we've got a 3-layered landscape with the trees at one level, binary, non-binary, and forests, sets of partitions, and then corresponding sets of diagrams. The Brauer diagrams, unbalanced ones, and the partition diagrams. And then this condition on the diagram. So if I go back here, you've got a singleton that's stuck on its own, because that was one of the roots of one of the trees in the forest. So if you have a tree, a non-binary tree, you'll have diagrams where every node is connected to another node, and here you release that condition. And that's where I'm going to end it. So thanks very much. So there's Peter, and there's James, who was very helpful with the semigroups, because it's not my wheelhouse. And there's our paper. So thanks very much.
Thank you for a great talk. Do we have any questions for you?
Yeah.
Have you looked at skew Boolean algebras at all?
At which ones?
Skew Boolean algebras?
No, I haven't. Sorry, you'll have to tell me what they are later on.
And also, you're taking the, I just realized it's taking the subsetting group, you're taking a subsetting group, which is a regular band or something like that, I think.
Okay.
It satisfies the equation that you mentioned.
Okay. Yeah. We took a few liberties, hopefully not with the mathematics itself, but with simplifying things for ourselves, just to try to, like, it's a game for us of taking, like, trying to get something biologically meaningful and something that mathematically we can work with. So I think, like, for all of these things, you can and should explore, like, different related structures and also more general structures. But I guess it depends what your goal is going to be. So like, if I could draw an analogy with theoretical physics and pure maths, like, there's a lot of, like, quantum group theory was motivated by quantum mechanics a long time ago, but then that whole area of mathematics just went off on its own and had a great time. And then what they did was often applicable elsewhere, but that wasn't their primary motivation. And I think this is sort of, feels like a lot of biological problems. It's really early days in the use of mathematics. I mean, there are lots of very canonical uses of differential equations and obviously statistics in biology, but I think in using algebraic ideas, it's still early. So maybe, actually, there's a great quote by I think his name's Sam Cohen. You may have heard this. He said, biology is mathematics next physics, and mathematics is biology's next microscope. So I mean, it's a brand. It's a branding statement, really. But there's something in there. So maybe there'll be more there. Thanks.
There was a question on Zoom. Andrew, if you could read it out, great.
Thank you. One question: can one endow the layers of the tree with some information, for instance, time? Yes, so that's a good question. So the trees do represent time. Yeah, that's definitely the case. So so you can think of a tree with weights on the edges, and those weights might indicate time. So I don't know how you would incorporate that information into this sort of way of thinking. So I guess for us, when we have a tree without weights on the edges, we do have some notion of time because you've got a hierarchy. So if you've got a node that's below another node, it's happened after that, something has happened. A speciation event has happened after the first one. So you've got some relative timings, but you can't say anything about pairs that separated that are not vertically related to each other. Unless you put weights on the edges, but you can do that, and people certainly do that, absolutely. Yeah, and I guess, oh no, I won't go there. There's a whole lot of theory in phylogenetics about how to construct such trees.
Any other questions for Andrew?
Instead of the sandwich composition, you could make it a category. And Brauer diagrams.
Yeah, but then how do you multiply them?
You compose them only when the domains and codomains
match up. Yeah. But I think, like, so for us, we always have a larger, if you think of the top as the domain and the bottom as the codomain, that we always have a larger domain because that's the leaves. and the set of internal vertices is bounded above by n-2. Like it's only going to get smaller. So we never have a matching, yeah. Although you could allow multiplication of different sizes of trees. Yeah, so if you had a tree on n leaves, you could multiply it by a tree of smaller number of leaves. Yeah.
You want like times to match up, right? Like you wouldn't want to multiply across, but maybe that's already taken into account.
Times, yeah.
But if you're multiplying trees, then you wouldn't want nodes to match up if they're at completely different times. Right?
Yeah, look, I already don't know what multiplying the trees means. So, like, I wouldn't want to like get too far down a rabbit warren of meanings. I mean, one weird thing about multiplying the diagrams without flipping them is that you're multiplying, you're connecting the internal vertices of one, which is along the bottom, with the leaves of another. So what does that mean? I mean, maybe it means something. Maybe in the trees, you're sort of slicing off some part of one tree and you're joining the leaves onto the other one. Maybe that does.
Vertical gene transfer.
Vertical gene transfer. That's weird.
I mean, like bacteria or something.
Yeah.
Transfer, like,
Yeah. I mean, that usually happens horizontally. So, all right. Yeah. Yeah. So, yeah. So, absolutely. So, well, okay. So that's another question that I'm working on right now. You know, so not exactly that question, but so I've been working a lot on phylogenetic networks, and networks are valuable for representing things like horizontal gene transfer and hybridization. So trees can't represent those sort of very common phenomena at all. So my question then in this context is, what do you have if you don't have partitions of a finite set? So I think I've proved that you get some covers of a finite set with some, but you have to have very specific properties on the covers. If you want to have a correspondence between networks and some set theoretic structure, networks are a huge family. They're infinitely many on n leaves. So you have to constrain them somehow. You have to do all sorts of funny games, and you have to then think carefully about what your covers are. So it's not really.
Everything's still discrete.
Yeah, I mean, it is in my world because that's like the way I think. Yeah, but I mean, networks, you can definitely think about them as discrete objects. You throw away discreteness when you think of processes down a branch. So you think of a Markov process down a branch, and there are some parameters involved, and a continuous time, and a stochastic process. So yeah, I mean, I've worked on those a little bit, but only with people who really know that stuff. I don't understand.
Even then, though, we have punctuated in people.
Yes, I mean yeah, definitely. Yeah, you definitely don't have. It's not as smooth. So, yeah, no, that's good questions there. Yeah.
Okay, I think it might be a good wrap up. I think people need to get to class, but let's thank Andrew again, and thank you all for coming.
It's just no idea what time it was.
No, perfect.